Hi, my name is Aditya Nandy, and I'm a fourth year graduate student in Professor Heather Kulik's group. And today I'm going to be presenting about open shell transition metal compounds that can break strong scaling relationships for methane activation for methane to methanol. But first, I'd like to thank the organizers in Computational Catalysis 1 for giving me the opportunity to speak in this session. So every year, 135 billion cubic meters of natural gas are flared, and the majority of that natural gas is methane. And so if we can convert that methane into transport-friendly methanol, then we can harness a drastically underutilized resource. So in biology, methane monooxygenase proteins can convert methane selectively into methanol on isolated copper or iron cores. In synthetic inorganic chemistry, the periodic catalyst can convert methane into methanol with high 1-pass conversion and selectivity, although the conditions required for this catalyst are very harsh. They require sulfuric acid, for instance. More recently, some zeolite design has been done to try to mimic the active sites, the copper active sites exhibited in methane monooxygenase proteins, and these zeolites also show activity for methane to methanol. So all of these have a couple things in common. The first is that the reactivity occurs at one or two isolated metal sites. They all face challenges with simultaneous tuning of selectivity, activity, and stability, and many of these compounds have open shell electron configurations, which complicate structure-activity relationships. And so we are interested in investigating whether transition metal complexes with base metals or 3D transition metals that are more earth abundant can facilitate the reaction energetics that are necessary for conversion of methane to methanol. So if we take a look at early to mid-row 3D transition metals such as chromium, manganese, iron, and cobalt, catalysts in oxidation states 2 or 3, the methane to methanol energy landscape has a couple steps. The first is that we would need to form a high valent oxo intermediate in an oxo formation step using a 2-electron oxidant such as nitrous oxide. And after we form the high valent oxo intermediate, that oxo intermediate will be able to pull a hydrogen atom off of methane, which is very difficult to do, in the hydrogen atom transfer step here to form the hydroxyl intermediate, after which we're left with a methyl radical. And that methyl radical can then combine with the hydroxyl intermediate to form the methanol species, which is the product that we desire in the radical rebound step. And then that methanol species can be desorbed off of the methanol bound intermediate to return the catalyst to the resting state in the methanol release step. So in the realm of heterogeneous catalysis, computing all of these different reaction energetics independently is computationally expensive. So to reduce the cost of catalyst screening, there have been many studies on catalyst design using descriptor-based reaction energies. So that way you would compute one descriptor, such as the oxoformation energy, and correlate it with the rest of the energies on the reaction energy landscape so that you don't have to do explicit computation for the future energy landscape steps, and that you can get a pretty accurate result just based on the descriptor. And so that way you would build up a volcano where you have the potential determining step here, as well as the reaction energy that is your descriptor here. So in this case, the oxoformation energy. And you would build a volcano plot, and you would want to find something at the top of the volcano plot, which is your goal here for inverse design. And you would find a catalyst that has an optimal reaction energy for this reaction. So in our previous work, we found that due to the accessible spin and oxidation states of 3D transition metal compounds, descriptor-based screening really starts to not generalize over multiple reaction energy steps. And so we previously showed that descriptor-based screening fails for screening catalysts with optimal oxoformation energetics, but now we're going to extend this work to look at all other steps on the reaction energy landscape. And so to do that, we need to first build a data set. And so we do this with the mid-row transition metals that I mentioned, and we consider multiple spin and oxidation states. And just to give a quick foray into why we are considering that, I'll take a look at iron 4 and iron 5 oxo intermediates, which have D4 and D3 electron configurations respectively. And so if we look at the qualitative D energy d orbital energy diagrams, we can look at the respective d filling of the oxo intermediates. So with the 4 electrons and the 3 d electrons, we get different d fillings based on spin state. So here We have the high spin state and low spin state of iron 4 oxo, and the intermediate spin state and low spin state of iron 3 oxo, and we get different D fillings based on the spin state. And then the reason why this is important is because for hydrogen atom transfer energies, for instance, we are transferring a hydrogen atom, so a proton and an electron. And where that electron ends up on the metal oxo intermediate is going to be dependent on the spin state. So if we take a look at the hydrogen atom transfer energy, which orbital that electron ends up will be distinct based on the spin and oxidation state of the compound. And this isn't only true for hydrogen atom transfer energy. The rebound step that I previously showed also carries an electron in the methyl radical, and where that electron ends up will also be dependent on the spin state. And based on these differing positions in which these electrons can end up, we may see different behavior, and that is what we set out to probe. In addition to the spin and oxidation state behavior, we wanted to make sure that conclusions we were drawing were based on a wide variety of commonly studied small ligands. So in this case, different coordinating atoms with these monodentate cell ligands. And we also looked at the impact of studying more macrocyclic type ligands, where we have primarily nitrogen and oxygen coordinating compounds that are seen more in the experimental literature. We also looked at the impact of varying the ligand configuration, so we can allow up to 2 ligands in this space, and we end up with a space of roughly 1,400 compounds over which we analyze reaction energetics. So the first step is to take a look at whether reaction energetics are a strong function of spin state. And so if we take a look at 2 different reaction energies, on the left side, we have the oxo formation energy, and on the right side, we have the hydrogen atom transfer energy. We see first metal dependence. So in this case, we're showing all low spin behavior for oxidation state 2, and we see strong metal dependence that recovers some intuition. So in this case, as we go to later transition metals with the low spin state, we see decreased stability for oxo formation, which recovers the concept known as the oxo wall, which tells us that it's harder to form a stable metal oxo on later transition metals. For hydrogen atom transfer energy restricted to low spin states, we see a boomerang style behavior where iron shows the most favorable reaction energetics for low spin for hydrogen atom transfer. If we then look at the spin state dependence on these energy landscapes, we see distinct behavior. So if we take a look at the intermediate spin species for oxo formation, we see similar trends to what we saw for the low spin state, but we do not see similar trends for the hydrogen atom transfer energies, where on the intermediate spin state, the reaction energies are roughly independent of the metal. And for some species, we also have the high spin states, and we can take a look at that as well. But looking at each individual step on its own is valuable in looking at the distributions, but we want to take a look at the joint distribution of these 2 reaction energies, for instance. And so if we take a look at the joint distribution, where we have oxo formation energies on the x-axis and hydrogen atom transfer energies on the y-axis, and we take a look at the kernel density estimate here that's plotted as a function of the variety of ligand fields that we considered, we see a distinct spread on this energy landscape, where we see 2 distinct clumps for cobalt and iron on this energy landscape. And so if we were to take this energy landscape and draw a single line through it, we would be missing a large proportion of these cobalt and iron catalysts. And so if we take a look at the explicit scatter plots upon which these kernel density estimates are built, specifically for iron and cobalt here, we see strong dependence on spin and oxidation state. So low spin iron 2 and low spin cobalt 3 catalysts end up in this kind of zone, whereas all other cobalt catalysts end up in this zone, and intermediate and high spin iron 2 catalysts and all other iron 3 catalysts end up in this zone. And we see less of this splitting in behavior in terms of spin and oxidation state on manganese. So what this tells us is that each metal has a distinct spin and oxidation state dependence, and a single global linear free energy relationship will fail to be predictive over all data. And so after observing this behavior, we wanted to compare our linear free energy relationships to those that have been already reported in the literature. So what I'm going to show is the slope of those lines that I plotted in the previous plot as a function of spin and oxidation state. And so the tan line here represents the values of the slope that have been observed in the literature, and the cyan line right here shows a global fit over all data. And so we can see right away that the global fit over all data doesn't match with the previously proposed linear free energy relationships. If we first plot oxidation state 2 catalyst, we see again the strong spin state dependence that I mentioned before on the scaling behavior, which comes out even further if we look at the oxidation state dependence. So if I focus on chromium over here, we see that for chromium 2, there's distinct behavior between the singlet and the triplet ground states, but triplet chromium 2 behaves similar to doublet chromium 3. But these observations do not necessarily hold across metals. But one thing we do observe consistently is that as we go to later transition metals and higher spin states, we observe steeper scaling behavior. So for instance, higher spin states of iron and cobalt compounds show more variation in hydrogen atom transfer energy for a given oxoformation energy. And so in addition to this distinct scaling behavior by metal and oxidation state, the spin state can also play a role in which parts of the energy landscape are accessible. So if we consider the convention of spin allowed energy landscapes, where the intermediates that are occurring throughout the energy landscape have the same ground spin state, we can subset out the reaction energies that have spin allowed energy landscapes. And we see that a linear free energy relationship will fail even more at identifying compounds that have spin allowed energy landscapes. And we see that in this case, manganese data shows the best reaction energies for both hydrogen atom transfer and oxoformation energy, shows the most favorable reaction energetics. We may also consider spin forbidden catalysts where for instance, one of the ground spin states changes for these intermediates. So in this case, 3 of the intermediates have high spin ground states, whereas this high valent oxo intermediate has an intermediate spin ground state. And if we consider the lowest energy pathway, we still see that drawing a linear free energy relationship through this data with a single line would be a gross oversimplification in looking at these reaction energetics and would fail to identify that there are manganese 3 catalysts that show this favorable behavior, even with this spin forbidden reaction energetics. If we take a look at the completely closed shell energy landscape, however, we see more distinct behavior that is more representative of a linear free energy relationship. A single linear free energy relationship. But for 3D transition metals, the reason why this is important is often the closed shell solution is not the ground state. And so the different conventions of spin here, the spin allowed and spin forbidden reaction energetics, lead to different energy landscapes and correspondingly show that the oversimplification of a linear free energy relationship would not allow us to be predictive. We can further place experimentally known compounds on this energy landscape. So this is the theoretical energy landscape that I showed before. And we can see that the experimentally derived compounds do not sit in a straight line on this set, and they sit within the bounds of the compounds that we've simulated. And so these are a variety of macrocyclic compounds here, primarily nitrogen coordinating and iron-based chemistry. And if we wanted to infer some design rules from where these compounds sit in the space, we can take a look at where iron-nitrogen compounds sit relative to the theoretical iron-nitrogen compounds that we simulated. And we can see that they sit relatively close. And so while a linear free energy relationship would not necessarily give us any insight on design, we can see that if we take a look at where our hypothetical iron oxygen compounds sit, we could actually improve the catalysts in theory if we went out and seeked iron oxygen compounds. And so in conclusion, what our studies tell us is that there's strong spin state dependence on reaction energetics, that linear free energy relationships are a bit of an oversimplification in open shell transition metal chemistry. Certain fragments of the energy landscape are accessible as exposed by consideration of different ground states. And over comparing the overlap between realistic experimentally derived catalysts and our theoretical catalyst space can give us insight into design rules that would be otherwise difficult to identify. And with that, I'd like to plug our preprint, which is now on Chem Archive. And I'd like to thank my advisor, Professor Heather Kulik, and the rest of the Kulik group, as well as you for checking out our talk. Thank you.